Hello and welcome to the video lecture for topic 15, substitution reactions of alcohols. Now, in our discussion of the substitution reactions of alkyl halides, we made the point that the leaving group on the electrophile must be a weak base. And this is why chlorine, bromine, and iodine are good leaving groups, but fluorine is not. So we can briefly summarize our substitution type reactions as follows, right? We have the two types of reactions we've seen so far, SN1 and SN2. Now, we're only going to look at three of the different factors here, but we know that there are a lot more that are involved. So the three factors that I'd like to take a look at are first, the type of the electrophile, right, the type of nucleophile, and finally, the solvent. So for SN1 reactions, our electrophile is going to be benzylic, allylic, tertiary, or secondary. Right? We know that the preferred nucleophile for SN1 reactions is going to be a weak base. And finally, that these reactions are promoted by polar protic solvents. Now for SN2s, our electrophiles here are going to be, our preferred electrophiles are going to be methyl, primary, and secondary electrophiles. Our nucleophile is preferentially going to be a strong base, and that these solvents are promoted by polar aprotic solvents. Okay, so that allows us to now consider how alcohols could serve potentially as an electrophile in a substitution reaction. So the first thing that we have to remember is that to be eligible for a substitution reaction, right, we have to have that electrophilic carbon be an sp3 hybridized carbon that has a polarized bond. And so if we take a look at a generic alcohol, we see that that condition is met. So here, a generic alcohol. This bond is polarized. The carbon-oxygen bond is polarized, which means that the carbon atom bonded to the hydroxyl group carries a partial positive charge, and the oxygen has a partial negative charge. Okay, so we do have a sp3 hybridized, right, electrophile here as our starting point. Next, we need to examine the leaving group. And so here our leaving group is OH minus, right? And when it dissociates, either through an SN1 or SN2 mechanism, we're going to end up with a strong localized charge on that leaving group. Right, and so now here, OH minus is going to be a strong base because its conjugate acid pKa is approximately 18, right? And so the conjugate acid is a weak acid, which means this is a strong base, which makes it a bad leaving group. So if we want alcohols to participate in a substitution reaction, we need to figure out how can we take this bad leaving group and turn it into a good leaving group, right? And so we know from our discussion of acid-base chemistry that it is possible for an alcohol to serve as either an acid, proton donor, or base, a proton acceptor, because the oxygen atom, right, has a lone pair of electrons that can accept a proton. Right? And so this means we can protonate this alcohol, but we need to use a stronger acid, right? A strong acid to protonate this alcohol. So we need something that's going to have a pKa less than -2, right? So I'm going to clear off the board, and we're going to take a look at what that means. So, as I was saying, we need our alcohol to be protonated by a very strong acid. So let's take a look at what that acid-base equilibrium would look like. I'm just going to start with a generic alcohol and some generic acid, HA. We know that our alcohols can serve as a base, that's what we're looking to do here, and we want to have a strong acid. Our products of this acid-base reaction, we can draw arrows to show electron movement and dissociation. We're going to form what's known as a protonated alcohol, or more commonly, we're going to form what's called an oxonium ion, and we're going to have the conjugate base of our acid. Right? So here now we can begin to label our species. Here we have our acid and our conjugate acid. Now we know from our pKa chart that the pKa of an oxonium is going to be approximately -2. So in order for the side of equilibrium that we want, our oxonium side, to be favored, our acid on our starting materials needs to have a pKa less than -2, right? So for this to be favored, here now we need a pKa less than -2 in order for this side of the equilibrium to dominate in this reaction. And so that means if we combine an alcohol with a strong acid, and this is typically going to be our mineral acids. So these are our HCl's, HBr's, HI, sulfuric acid, H2SO4, nitric acid, any of what we call our mineral acids, right? If this is what we're going to use as an acid, the oxonium side of this equilibrium is going to be favored. The consequence of that, forming this oxonium ion, is going to be very, very beneficial if we want to use an alcohol in a substitution reaction. Because now, if I redraw this alcohol this oxonium a little bit differently, I'm just going to put any old R groups on that electrophilic carbon. Now, when this dissociates, our leaving group, we're going to have some sort of, now I'm just going to use an SN1 process here for this dissociation. So I'm going to form a carbocation, right? Our leaving group is water. Now, water, right, is a weak acid. So as an acid, it has a pKa of approximately 18, right? However, if we think about this in a different way, if we think about water acting as a base, right, we can ignore that its acid pKa is 18. If we think of it serving as a base, its conjugate acid, H3O plus, is going to have a pKa of approximately -2, right? pKa of approximately -2. H3O plus is a strong acid, which means that H2O is a weak base, and therefore a good leaving group. So now, by using a strong mineral acid to protonate our alcohol and form an oxonium, we have created a species, our oxonium, that is able to participate in substitution reactions, since its leaving group is a weak base. Right? And so, now that we can use alcohols, now that we have one method, the first method that we're going to look at, by which we can use alcohols for substitution reactions, the next thing we want to do is consider some of the properties of what substitution reactions under these conditions are going to look like. So I'm going to clear off the board, and we'll be right back to take a look at that. So I'm going to write up the overall transformation, the overall substitution of an alcohol when treated with one of our hydrohalic acids. So this is going to be either HCl, HBr, or HI. And so the overall transformation, we start with ROH. We're going to add to that HX. And whether we go through an SN1 process or an SN2 process, we're going to end up with an alkyl halide, Ri, and our byproduct will be water. So now when we look at this, for a primary ROH, the only acid that we're going to be able to use to do this is going to be HI, and this is going to proceed by an SN2 mechanism, right? Primary electrophiles always go through an SN2 mechanism. For, right, so we can do this by HI. Also for primary alcohols, we can also use HBr. However, we have to use that in combination with a second acid, sulfuric acid. And finally, this is also going to proceed by an SN2 type mechanism since we have a primary electrophile. For secondary and tertiary alcohols, we have a lot more options. And so for secondary or tertiary alcohols, we can use any of our mineral acids. So we can here now use HCl or HBr or HI, and all of these will proceed through an SN1 type mechanism. Okay, so far we've covered how alcohols behave in the presence of our hydrohalic acids, right? So this is HI, HBr, HCl. And really the only type of substitution we can do is to convert an alcohol into a alkyl halide. But what if we want to use some nucleophile that's not a halogen? What if we want to do some other type of substitution on this electrophilic alcohol? Well, we have to find a different way to convert our alcohol, our OH group, into a good leaving group, right? Because if we use one of these acids to activate it to form that oxonium, the conjugate base of these acids, the halogen anion, is going to be a good nucleophile, and so it's going to go ahead and intercept, right, whether it's the primary oxonium in an SN2 or it's going to intercept that carbocation in an SN1, and we're not going to be able to get some other different nucleophile to do the substitution. And so the other way that we can convert these alcohols into a good leaving group is to form what's called a sulfonate ester. And so sulfonate esters are formed in their own independent reaction before the substitution is conducted in a second separate reaction. And so to form a sulfonate ester, we start with our alcohol, and I'm going to now denote the different R groups as R1 in our alcohol. We use what's called a sulfonate chloride or a sulfonate anhydride that has a general formula that looks like this. I should say a general structure that looks like this. Can't forget my electrons on chlorine. And it's got some other R group which we're going to call R2. The alcohol and the sulfonyl chloride or the sulfonyl anhydride, as we'll see in just a little bit, are treated with a very mild base. Typically this base is either going to be pyridine or triethylamine to form our sulfonate ester. So now we have the R group from our alcohol we have the oxygen from our alcohol, we have the rest of that sulfonyl chloride, and it's R group, R2, plus our protonated base and a chlorine anion, which is a salt pair, right? And so we would have, I'm just now going to show this just for pyridine. We would have a protonated pyridine, and since that has a positive charge, we have to have something to balance it out so that our reaction, right, our total formal charge on one side of our reaction must be the total formal charge on the other side of our reaction. And so that chloride becomes the counter ion for our protonated pyridine. I could have also used triethylamine, so this is one or the other, and we end up with this same result with protonated triethylamine instead of protonated pyridine. This here, right, this new molecule that we formed is known as a sulfonate ester. And the nice thing about sulfonate esters is that they actually have built into them a really great leaving group. And so I'm going to box that leaving group now in a different color so that you can see what I'm talking about. So here now this becomes the leaving group. So again, this is one reaction that we do first. We isolate this entire sulfonate ester and purify it. We take that separately. So now we're going to take that sulfonate ester, and in a second reaction, we start with our sulfonate ester. We have some sort of nucleophile, and we can now convert this to our substitution product, where now the R group, the alkyl group that came from our alcohol, is bonded to our nucleophile, and our sulfonate ester falls off. And this shows us why sulfonate esters are so good for substitution reactions. We see here now that our sulfonate ester looks very similar to the conjugate base of sulfuric acid. And if you recall from lecture, we talked about how the conjugate base of sulfuric acid is not only a very weak base, so this is a weak base, it's a good leaving group, but it's also a very poor nucleophile because this negative charge is delocalized across all three of the oxygen atoms. And so now we have both a weak base and a weak base and a poor nucleophile, and so these are very favorable transformations, right? Using sulfonate esters is a great way for us to do substitution reactions. And I've written these as two separate reactions because, as I've said before, the first reaction to form the sulfonate ester, we actually stop, fully purify that sulfonate ester, get rid of our byproducts, and then in a separate step, treat the sulfonate, or a separate reaction, treat the sulfonate ester with a nucleophile to get our final desired substitution product, which is boxed right here. Okay, so we're going to go ahead now and take a look at the three different types of sulfonate esters and the reaction conditions to produce them. So I'm going to clear off the board, come right back and show you those. So there are three sulfonate esters that are primarily used to convert alcohols into good electrophiles for substitution reactions. And those are going to be tosylates, mesylates, and triflates. And they're all pretty similar, and we have very similar reactions that we use for them. So to form a tosylate, we begin with our alcohol, and the reagent that we combine it with is known as tosyl chloride. which has this structure. Again, we can use either pyridine or triethylamine, so I'm just going to write weak base over my arrow. And that's going to give us our tosylate ester that looks like this. So these are our tosylates. And the name of this reagent is, well, the name of this reagent that we'll work with here in Chem 201, we're just going to go ahead and call this tosyl chloride. Now, for our mesolates, we have a very similar reaction. Again, we're going to start with an alcohol. This time, however, instead of tosyl chloride, we're going to use what's called mesyl chloride. It has a very similar structure to tosyl chloride. We have similar reaction conditions where we use a weak base, either pyridine or triethylamine. This is now called mesyl chloride. And that produces for us, right, our mesolate that we can use in substitution reactions. Now, triflates are a little bit different. Triflic chloride is a very unstable and dangerous reagent. And so when we're preparing a triflate, instead of using triflic chloride, we again start with our alcohol, but this time we use triflic anhydride, which has this structure. So this is triflic anhydride. Again, these reagents are combined in the presence of a weak base. To give our triflate, excuse me, which is, once again, an excellent candidate for substitution reactions. Now, there's going to be a second half to this video lecture where I go through the reaction mechanisms that you're going to need to know. And so I'm not going to get into the specific mechanisms of these three transformations here. We actually have quite a few different reaction mechanisms associated with this topic. And so I'm going to do a part 2 video lecture where I go through step by step all of the mechanisms you're going to need to know. I will give you a warning right now. The arrow pushing mechanisms in sorrel you should always ignore. I do not agree with sorrel's arrow pushing. Sorrel takes a lot of shortcuts and skips a lot of steps that are very important for us to show in our reaction mechanisms. The reason I'm going to ask you to ignore sorrel's arrow pushing and stick with my arrow pushing only is because this is going to prepare you for the arrow pushing you're going to need to do in Chem 202 as well. And so we're going to have a second part to this video lecture where we just talk about each of the mechanisms, right, for the different reactions we're going to see here so far. So getting back to what we have here up on the board, right, we now have a way to produce 3 different sulfonate esters, tosylates, mesolates, and finally triflates. And all 3 of these are excellent candidates, right, for substitution reactions. So there are 3 more reactions I'd like to show you, right? Don't really fit into the categories that we've seen so far, right? It's not really treating an alcohol with hydrogen halide type acid. It's not a substitution that involves an alcohol being first converted into a sulfonate ester. But these are reactions that are used frequently in organic chemistry. And again, these are going to be reactions you're expected to know for Chem 201. Okay, so I'm going to clear this off, and we're going to take a look at those last three reactions here in just a moment. So at the beginning, in the first part of this video lecture, at the very beginning, we saw how we could use hydrochloric acid or hydrobromic acid to convert an alcohol into an alkyl chloride or an alkyl bromide. We also have two other reagents that will allow us to make these same transformation happen, but it prevents us, or it allows us to avoid using a strong acid like HCl or HBr. And as we move through this semester and next semester, we're going to see that there are a lot of instances where we'd like to make this conversion happen, converting an alcohol into either an alkyl chloride or alkyl bromide, but based on other functional groups in the rest of our molecule, it may be detrimental to use a strong acid. And so if we'd like to convert an alcohol, and now this is going to be, I'm only interested in you knowing the mechanism for primary and secondary alcohols, which we'll see in part 2, but we can also do this with tertiary alcohols. But if we treat an alcohol with a reagent known as phosphorus tribromide, so this is going to be PBr3, and I'm going to go ahead and put all of my electrons in so that we see what the full Lewis structure of this reagent looks like. That will result, right, in us producing a alkyl bromide. And we'll see in part 2 how this reaction proceeds, right? And we'll see the arrow pushing mechanism and the byproducts that are produced. Now, we could take an alcohol and treat it with hydrochloric acid under the right conditions to produce an alkyl chloride. However, as I mentioned, there may be some circumstances where we don't want to do that, and so because the strong acid HCl may be detrimental to some other part of our molecule. And so we can also get this overall transformation to occur by treating with a reagent called, right, sulfonyl chloride, or sorry, thionyl chloride. So here, this reagent, I'm going to go ahead and once again put in all of my electrons so we see the full Lewis structure. Right, so this is thionyl chloride. When we use thionyl chloride, we need to use this with a weak base. Again, our weak bases are typically pyridine or triethylamine. And overall, this reaction will produce for us an alkyl chloride. I'm going to take a moment and show you here the other products that are formed, right? So one of our other side products is going to be SO2, which is a gas. And then finally, let's say I use pyridine for my weak base. I'm going to have the last product, or the last side product, byproduct of this reaction, is going to be that protonated weak base with the other chlorine ion as its counter ion to balance charge. So now we see we can also generate alkyl bromides by using phosphorus tribromide. So again, this reagent is phosphorus tribromide, and that gives us an alkyl bromide. We can take our alcohols, treat them with thionyl chloride in the presence of weak base to generate alkyl chlorides. And the last reaction I'm going to want to show you is our first what's called named reaction that we're going to encounter in Chem 201 and 202. And this is known as the Mitsunobu reaction. And it is named for the chemist who discovered it, Mitsunobu. I forget his first name at the moment, so you'll have to forgive me there. Now, the Mitsunobu reaction is only for primary or secondary alcohols. And I'm just going to show you the overall reaction scheme right now, and we're going to get into the mechanism of topic 15, part 2 video lecture. So the overall reaction, we begin with a primary or secondary alcohol. Again, this has to be primary or secondary. Tertiary alcohols do not participate in the Mitsunobu reaction. We're going to have some sort of an acidic nucleophile. And so now the pKa of this acidic nucleophile, right, the pKa of this hydrogen needs to be somewhere between 5 and 12. So again, this pKa is going to be greater than or equal to 5, less than or equal to 12. And then we use two other reagents in this reaction, right? We also need to use what's triphenylphosphine. Again, remember that pH is the abbreviation for a phenyl ring. So we use triphenylphosphine plus a reagent that we call DEAD. And yes, we literally call it DEAD. DEAD, D-E-A-D, stands for diethyl azo dicarboxylate, and it has a structure that looks like this. And we'll make this a proper Lewis structure so that when we get to our arrow pushing, we know where all of our electrons are. All right, so we take a primary or secondary alcohol, we take a weakly acidic nucleophile with a pKa somewhere between 5 and 12. So representatives of these nucleophiles would be our carboxylic acids, right? We can do our phenols. We can use thiols. We can also use weak acids like HCN or HN3, right? So these are all nucleophiles that are acidic that have a pKa somewhere between 5 and 12. And then the two other reagents we need are triphenylphosphine and DEAD. And overall, this transformation, and I'm running out of space here, so I'm going to make a little space right here while I tell you this, right? Overall, this transformation, this combination of reagents, is going to result in a substitution reaction at that alcohol where we replace the OH group with our nucleophile, or the conjugate base of our acidic nucleophile. So overall, this transformation will produce for me our nucleophile. We're going to see in part 2 that this proceeds through an SN2 mechanism, and that this product will result in an inversion of stereochemistry. Our byproducts from this reaction, right, are going to be triphenylphosphine oxide, and we're actually going to end up protonating both of the nitrogens on DEAD to give our second byproduct, which has a structure that looks like this. Excuse me. Single bond there. Let's clean up how that nitrogen looks, huh? And here are all of our electrons in the byproduct formed from DEAD. Okay, so that covers the reactions and transformations of alcohols when they participate in substitution reactions, right? We've seen what the starting materials look like, the reagents we use. We've seen how to use, right, our mineral acids to form oxoniums, which can undergo substitution. We've seen how to use sulfonyl chlorides and sulfonyl anhydrides to be able to convert alcohols into sulfonate esters, which can participate in substitution reactions. And we've seen three last ones that don't fall into those first three categories: the use of phosphorus tribromide to convert an alcohol to an alkyl bromide, the use of thionyl chloride and a weak base to convert alcohols to alkyl chlorides, and finally the Mitsunobu reaction, right? We've seen these to do substitution on alcohols. We've seen the starting materials and products for all of these transformations. So I'm going to stop this video lecture here, and then we're going to have a part 2 for topic 15, where we actually look at each and every one of the arrow pushing mechanisms for all of the transformations we've seen. Now, you should be aware that you will be expected to know the arrow pushing mechanisms for all of these reactions. And this is why I'm going to have a part 2 where I go through them with you step by step. The arrow pushing that I use in part 2 is the correct arrow pushing. The arrow pushing in Sorrel is the incorrect arrow pushing. You will be expected to use the arrow pushing that I show in video lecture part 2. All right, thank you very much, and I'll see you in part 2.